In this lecture, we're going to cover section 1.1, angles and radian measure. Now, this is from chapter 1 of trigonometry. I don't want you guys to be confused. The way the book is, the first part of it, the chapters are for algebra. And then the last couple of chapters in the book are for trigonometry, but it starts at chapter 1 again. So even though this is chapter 1, it's the trigonometry chapter 1. So if you're following along with the textbook or with the ebook, I just don't want you to think that this is the same chapter 1 that we already covered. This is towards the end of the book where the trigonometry begins. So we're going to start with angles. Some of this will be a review. So let's just talk about the definition of an angle. An angle is just formed by two rays that have a common endpoint. So this example that we have right here is an angle. And a lot of times we use theta to measure an angle. So this symbol right here is theta. We could also use capital letters. We can use alpha, beta. So for example, this would be alpha, this is beta. So we'll see them throughout the text, but I feel like the most common one is theta. Now, we have one side of the angle, which is called the initial side, and then the other ray is called the terminal ray or the terminal side, and they meet at the vertex. So an angle is in standard position if its vertex is at the origin when we're talking about the rectangular coordinate system, and its initial side lies along the positive x-axis. So here's an example right here. So you see how we have the XY coordinate system? If we start at the origin and if the horizontal x-axis, think about that as the initial ray, the initial side of the angle. If we open counterclockwise, like we're doing in this picture, we just formed an angle, right? And this angle is being called alpha. So we have angle alpha, and the terminal side of the angle you see is in the second quadrant. So just to kind of get a head start, and we'll get to this later on, but remember, we could think of the XY coordinate system, right, as breaking into 4 quadrants, right? So we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4, just as a reminder. So if we have an angle whose initial ray coincides with the x-axis and we open counterclockwise, that angle is going to be positive. So this here is a positive angle. However, it is possible to have an initial ray, an initial side, but if we rotate clockwise and form an angle, like in this case, theta, now the terminal side, you see how it's living in quadrant 3, but since we opened clockwise, this angle is going to be negative. So it's a negative angle measure. So angles can be positive or negative, just depending on if the angle was formed by turning counterclockwise or clockwise. So let's look at the next page, just to kind of continue our little introduction on angles. And I did say this, but we'll just review it again. So when we see an initial side and a terminal side in place, there's two kinds of rotations that could have generated the angle, either rotating counterclockwise, and we said that would produce a positive angle, or a negative angle could be generated by a clockwise rotation. So that's what I explained in the slide above. And this is just over here, just another representation of that. It's the same picture that was above. So that's the difference between a positive and a negative angle. And an angle is called a quadrantal angle if its terminal side coincides with one of the axes. So let's look on this example right here. You see how we have the initial ray. We opened counterclockwise to form this angle right here, beta we called it, but you see how the terminal ray is landing on the y-axis? So if the terminal side lies on either the x or y-axis, we call this a quadrantal angle. So this is an example of a quadrantal angle. So now let's talk about how we measure angles. I think the most common measure that a lot of you are familiar with is degrees. We're going to cover both degrees and radians, but I feel like degrees are easier to understand because that's how, when you guys are introduced to angles, that's how you learn how to measure them in degrees. So let's just start in terms of degrees. So angles are measured by determining the amount of rotation from the initial side to the terminal side. A complete rotation of a circle is 360 degrees. So for example, let's say here's let me do a different color so we can differentiate. Let's say this is my initial ray. And we open counterclockwise, but we go all the way around and we land right back on the terminal ray, the initial ray. So let's say the initial ray is the same or lies on top of the terminal ray. The terminal ray and the initial ray are the same, right? So that would be a 360 rotation, 360 degrees. So 1 degree is just 1/360th of a full rotation. That's how you got to think about degrees. So let's get rid of this. Let's draw a little blank canvas here. Now, what if we were to go a quarter of a rotation, right? So what if we were to form this angle right here, right? This would be a 90-degree angle, because we went 1/4 of the way around, right? Remember, one full revolution is 360 degrees. So if we go 1/4 of 360, or 360 divided by 4 is 90. So this would be a 90-degree angle or a right angle, right? 90-degree angles are right angles. So 90 degrees is that quadrantal angle that's formed when we do a quarter of a counterclockwise rotation. And then let's do a different color. If I wanted to do half a rotation, now my terminal ray is going to live on the x-axis, and I just went half of a rotation, or half of 360. So this angle that we just formed in green would be 180 degrees. That's also called a straight angle. So that straight angle measures 180 degrees. And just a review of acute and obtuse angles. So an acute angle measures less than 90 degrees. So an acute angle would be an angle whose terminal ray is in the first quadrant. And an obtuse angle measures more than 90, but less than 180 degrees. So an obtuse angle would have a terminal ray that lives in the second quadrant. So anything between 90 and 180 degrees. And then, of course, we said a right angle measures 90 degrees. So now that we said, okay, 1 degree is 1/360th of a full revolution, right? Because if we do one full revolution or rotation around the circle, that's 360 degrees. So now let's talk about radians. So how do we measure angles using radians? So an angle whose vertex is at the center of the circle is called a central angle. So you see in this example down here, and that's where every time we sketch an angle, we're going to assume um, it's a central angle, that the vertex is going to be at the origin 0, 0 when we're talking about the XY coordinate system. So the way we interpret radian measure of any central angle of a circle, it's the length of the intercepted arc divided by the circle's radius. So what does that mean? Well, let's look at this picture, and I'm going to make this picture a little bit bigger. So we have an angle here, right? Here's the initial side. Here's the terminal side, right? We form this angle by rotating counterclockwise. And we want to measure this angle in radians. Now, the way we measure it is, so whatever this angle theta is, it's proportional to the radius of the circle. So this circle has a radius, right? All circles have a radius. And the radius is the distance from the center, right, to the circle itself, right? So what's half the distance, in other words? That's the radius. And then the arc length, the length of the intercepted is right here. So this would be the arc length. So how far we would have to travel along the edge of this circle, right? From the initial ray to the terminal ray. That's the length of the arc that's created. So let me give you an example. So before we go down to the next page and do an example, let me just go back to this one for a minute. Let's assume that this is 1 radian. Let me just erase that so we could see this clearly now. So let's assume that this angle is 1 radian. And the radius, let's say, is equal to 1, and that's the same as the arc length, which is equal to 1. If we were to take 1 divided by 1, we get 1, and that would be the radian measure of this angle. But it's all proportional. Most circles that we're going to work with don't have a radius of 1. And then, it'll adjust accordingly when we divide out. So you'll see. So let's look at this example down here. So let's just say generally speaking now. So consider the arc length, we'll call it S. So typically in a lot of textbooks, so here's an angle theta right here, right? So it's this angle that's being formed. So here's the arc length, right? Here's the distance that we traveled along the edge of the circle to create this angle. So we call arc length S. That's just the typical notation that we use. And typically we use R for the radius. So here's the radius of the circle, right? And let me do that in a different color so it doesn't get confusing. So in red, here's the radius, right? Half the distance. So in order to get the measure of that angle, theta in radians, we take the arc length and we divide it by the radius. Like I said above, it's proportional. So let's do an example. So example 1 says a central angle theta in a circle of radius 12 feet intercepts an arc length of 42 feet. What is the radian measure of theta? So look, let's sketch a picture. And actually, let's not even make the coordinate system because then we're just going to have, I feel like, more grid lines than we need. So let's do this. So let's imagine we have a circle with radius r. And in this case, I'm telling you that the radius is 12 feet. So this radius r is equal to 12 feet. We're going to form an angle, a central angle, right? Because the vertex is going to be at the center of the circle. And we want to create an angle theta, and the arc length, the distance that we're going to travel, right, around the arc or the length of the circle is going to be 42 feet. So let's say we create this angle, and let's say this angle is theta, and we traveled a distance of 42 feet. So remember, we use S to represent arc length. So let's say the distance that we traveled in red around the arc is 42 feet. And we form this angle theta. So what is the measurement of theta? In other words, what's the radian measure of theta? So the way we get theta, right? The arc length is proportional to the radius, right? So it's S over R. So we're going to take S, which we said is 42 feet, and we're going to divide that by the radius, which is 12. Now, whenever we're talking the length of the arc compared to the radius, the result is always going to be in radian measure. So what's 42 divided by 12? It's 3.5. And remember, we were figuring out the measurement of the angle theta, and this is in radians. So that would be how we would figure out theta. If theta was in, formed in a circle, right? We have a central angle. And if we want to figure that out, if we know the arc length and the radius, we just compare the two. So 42 divided by 12, which is going to give us 3.5 radians. So now let's talk about how to convert between degrees and radians. And I think a nice way to explain this is the following. And actually, let me go to the whiteboard. So let's talk about the circumference of a circle for a minute. So in case you forgot, the circumference, or the distance around a circle, is equal to 2 times pi times the radius. And let's just, for simplicity, let's let the radius of a circle be equal to 1. So if that's the case, then we would have C equals 2 times pi times R, but R is 1, right? So the circumference is just equal to 2 pi. Now, remember what we said earlier. If we were to make one full revolution, right, or one rotation around the circle, that's 360 degrees. So then if 360 degrees, right, is one revolution, or if we would travel once around the circle, we can replace C, the circumference, right? Because that's the distance around the circle. We could replace that with 360, and that's equal to 2 pi. And now if we divide by 2, 360 divided by 2 is 180 degrees. 2 divided by 2 is 1. So 180 degrees is equal to pi radians. So in other words, let's say this is 0 degrees. And remember, 180 degrees is when we do a half a revolution, right? It's the straight angle. So let's say we made an angle of 180 degrees. That's equivalent to pi radians. So 180 degrees, if we were to convert it to radians, it's equivalent to pi radians. So let's look at this in perspective, actually. So before we go and practice converting between degrees and radians, radians and degrees, let's look at this. So this would be an angle of 0 degrees, right? If my initial ray was the same as the terminal ray, right? So if we didn't rotate at all, that would be an angle of 0 degrees. Now, we said earlier, let me just change colors here. If we went a quarter of the way and formed an angle, that would be a 90-degree angle, right? That quadrantal 90-degree angle. And we said if we were to go halfway, right, around the circle, that would be an angle of 180 degrees. And then let's go another quarter of the way. So to here, to this quadrantal angle, right? So now we're going 3/4 of the way to 360 degrees, right? One full revolution, or in other words, 180 plus another 90. So that would be an angle of 270 degrees. And we said if we do one full revolution, and I'll do that in light blue, right? We said one full revolution is going to be 360 degrees. So you could think of an angle of 360 degrees, the terminal ray, as sharing the same terminal and initial ray as a 0-degree angle. So that's why I wrote it as 0/360 degrees. But now let's convert these to radian measure. So we already said that 180 degrees is the same thing as pi radians. One's in degree measure, one's in radian measure. So then what would 90 degrees be in terms of radian measure? Let's think about that. Well, if 180 degrees, right, is equal to pi radians, half of that is 90 degrees, right? So take half of pi. So this would just be pi divided by 2. So 90 degrees is the same thing as pi over 2 radians. And now imagine what 270 degrees would be equivalent to in terms of radian measure. So think about what we're doing. Actually, you want to know what might make more sense first. Let's do 360 degrees as radians, right? That would be two sets of 180, right? Halfway and then halfway again. And 180 degrees is equal to 1 pi radians, right? So if we went twice, two sets of 180, that's going to be 2 pi, right? So 360 degrees is equivalent to 2 pi radians. So now if you want to interpret 270 degrees, 270 degrees is 3/4, right? That's a 3/4 rotation, 3/4 of the way around the circle. So it's 3/4 of 2 pi, right? We're going 3/4 of the way to 2 pi because 2 pi is one revolution. And the way we take a fraction of something is we multiply. So let's take 3/4 times 2 pi, or 2 pi over 1. That's going to be 6 pi over 4. And if we reduce that, that's 3 pi over 2. So 270 degrees is the same thing as 3 pi over 2 radians for that reason. Think about it as we're rotating 3/4 of the way, right, of one full revolution. And one full revolution in terms of radian measures 2 pi radians. So 3/4 of 2 pi is 3 pi over 2 when we reduce. So then the question becomes, how do we then convert any degree measure to radian measure, right? I just did it here for an example with the quadrantal angles, 90, 180, 270, 360. But how do we convert in general? Well, let's just use the fact that we know 180 degrees is equal to pi radians. So if I want to go from radians to degrees, and we know that 180 degrees equals pi radians, right? I want to go from radian to degree measure. So then let's think about this. What's 1 radian equivalent to? This is pi radians, but if I divide by pi on both sides, now I'm going to get 1 radian is equal to 180 degrees divided by pi, 180 over pi. So now, what if I wanted to convert 2 radians to degrees? Because this is 1 radian is equal to 1 pi over 180 over pi. 2 radians would be 2 sets of 180 over pi, right? Or 2 times 180 over pi. 3 radians would be 3 sets of 180 over pi, or 3 times 180 over pi. So the conversion from radians to degrees is take 180 over pi and multiply it by the number of radians that you're trying to convert. So that's how we're going to go from radians to degrees, 180 over pi times the radian measure. Now let's go the other way around. What if I want to go from degrees to radians? Well, remember, 180 over pi, well, actually, let's back up. Let's start with what we know, right? 180 degrees is equal to pi radians. Well, what's 1 degree equal to, right? So let's divide out by 180. So we're going to get 1 degree is equal to pi over 180 radians. So then 2 degrees would be 2 sets of pi over 180, or 2 pi over 180. 3 degrees would be 3 times pi over 180, and so on and so forth. So to go from degree measure to radian measure, we're going to take pi over 180 times the degree measure. And these are our 2 conversions. And that's what we'll use when we get back to the worksheet. So look, let's go back to the worksheet. And that's what I have here. So all we're doing is using that relationship that I told you about, that pi radians is equal to 180 degrees. So now to go from degrees to radians, we just said multiply the degree measure by pi over 180. And then to convert radians to degrees, we go the other way around, multiply the radians by 180 over pi, 180 degrees over pi radians. So let's practice. Let's look at the first, or example 2. Let's convert each of these angles in degrees to radians. So pi over, 60 degrees, right? So we're converting each angle in degrees to radians. So for 60 degrees, we're going to take 60, and then we're going to multiply that by pi over 180. So we're going to get 60 pi over 180. And if we reduce that, right, 60 goes into itself once and into 180 3 times, that's just pi over 3 radians. So 60 degrees is equivalent to pi over 3 radians. And let's look at B, 270 degrees. If we want to convert that to radians, we're going to take 270 and we're going to multiply it by pi over 180. So we're going to get 270 times pi over 180. And let's reduce. So 270 and 180 are both divisible by 90. So 90 goes into 270 three times and into 180 twice. So we're going to get 3 pi over 2 radians. And C, negative 300, the same conversion holds if it's a negative degree measure, whether it's positive or negative, you do the same thing. So we're going to take negative 300 times pi over 180, and we're going to get 300 pi over 180. And now we just have to reduce that. And 60 goes into both 300 and 180. So 60 goes into 300 5 times and into 180 3 times. So we're going to get 5 pi over 3 radians is equivalent to, and I'm sorry, negative. Let's not forget this is negative. So negative 5 pi over 3 radians is equivalent to negative 300 degrees. And now let's go the other way around. So now to convert radians to degrees, we're going to multiply the radian measure by 180 over pi. So for example, look at A, pi over 4 radians. So take the radian measure and multiply it by 180 over pi. And when the radian measure is written in terms of pi, pi over pi will just be 1, right? And now we're just going to have 180 over 4, which is 45 degrees. So pi over 4 radians is equivalent to 45 degrees. So let's try the next one. We have negative 4 pi over 3 radians. So we're going to take negative 4 pi over 3 and multiply it by 180 over pi. And pi over pi is 1. And we could also do 3 into 180 goes 60 times. So now all we're left with is just negative 4 times 60, which is going to be negative 240 degrees. We'll do one more. Look at C. Now this time, this radian measure is not in terms of pi. So radians don't always have to be written in terms of pi. This is just 6 radians. So the conversion is the same. So we're going to do 6 radians times 180 over pi. And then we're going to end up with 6 times 180 over pi. And you could plug that in the calculator. And we get about 343.77 degrees. And let me show you, you have pi in the calculator. So hold on, let me just open my calculator. So if we want to type in 6 times 180 divided by pi, you see how I did 6 times 180 now divided by pi you have in your calculator. It's above the division key. It's above the exponent key in blue, right? So we're going to do second and then the exponent key. And there's pi, right? So 6 times 180 over pi. So you never have to approximate by using 3.14. Use pi in the calculator. Your answer is going to be more precise. And that's where I'm getting 343.77 degrees. So you're not always going to get a nice round number when we're talking degree measure. Like in this case, we had to round it. All right. So let's talk about how we can sketch or draw angles in standard position. So we said that when the terminal side makes one full revolution, it forms an angle whose radian measure is 2 pi. Or if we were to do one full revolution, the angle measure in terms of degrees, the angle measured would be 360 degrees, right? And we already did this actually when I went to the whiteboard before, looking at the angles that are formed when we go a quarter of the way around, halfway around, 3/4 of the way around, right? So this we already did when we were on the whiteboard. So let's kind of just reiterate. So remember, a quarter of a revolution is pi over 2 radians. It's this quadrantal angle that's formed with the y-axis, and that's also equivalent to 90 degrees. And then we said, okay, if we go half a revolution, that's pi radians, which is equivalent to 180 degrees. We said if we go 3/4 of the way, right, that's going to be 3 pi over 2 radians, which is 270 degrees. And if we do one full revolution, that's 2 pi radians or 360 degrees. So we can use those as a guide when we sketch angles in standard position. Meaning if the vertex is at the origin of the circle and we either open clockwise to make a negative angle or counterclockwise to make a positive angle. So let's look at A. So A, we want to sketch 3 pi over 4. So this is how I think about it. So here's 0 degrees, right? Here's, or you know what? 0 radians, because we're in radians right now. So here's, and the reason I know that is because there's no degree symbol. So now let's just take a moment then to discuss, how do you know if an angle is given and it's in degrees or radians? Well, if you see the degree symbol, then it has to be in degrees, like D, E, and F. This is supposed to be F, not D. But you see how A, B, and C, there's no degree symbol, and the giveaway too is pi. Whenever an angle is written in terms of pi, most likely it's going to be radian measure. So that's the difference. So 3 pi over 4. Now you see what we're doing? This is the same thing as 3/4 pi. That's like taking pi and multiplying it by 3/4. So in other words, halfway would be pi, right? But let's go 3/4 of pi. That's really what we're doing. We're going 3/4 of the way to pi. So imagine breaking this upper half of the graph into quarters. Here's 1/4, 2/4, 3/4, 4/4. Because 4 over 4 is 1, right? So 4/4 pi would be 1 pi, but we want to go 3/4 of the way. So we're going to go 1, 2, 3, which is going to land us right there, right? If we go 3/4 of the way to pi. So that would be my angle, 3 pi over 4. That's what theta would be equal to. So the terminal ray would be in the second quadrant, because 3 pi over 4 is smaller than pi, right? Because it's only 3/4 of pi. Let's look at the next example, B. What if theta is equal to negative pi over 4? So again, we're dividing into quarters. That's why I'm going to use fourths. If my denominator was thirds, I would divide into thirds, and so on and so forth. So here's 0 radians, but now we're negative. So if I go halfway around now in the clockwise direction, here's negative pi radians. Now we want to go, this is like 1/4 pi, but negative, right? So negative 1/4 pi. So again, imagine dividing the lower half of the graph into quarters, 1, 2, 3, 4 quarters, right? I'm dividing pi into quarters. We just want to go 1/4 of the way around, right? Because it's 1 pi over 4. But since it's negative, we have to rotate in the clockwise direction. So if we go 1/4 of the way, this angle is equal to negative pi over 4. And let's do one more in radian measure. C is a positive angle, so we're going to open counterclockwise. Again, now we're going 7/4 of pi. Pi is here, right? It's this straight angle, pi radians. That's a half a revolution. Now we're dividing into quarters again. So what I'm going to do is I'm going to divide my top and bottom portion of the graph into quarters. And the reason I'm going into the bottom portion is because we want to go 7/4 of the way. That's more than one half a revolution to pi, right? Because 4 pi over 4 would be 1 pi, but we're going 7/4 of the way. So we need to count 7/4. So 1, 2, 3, 4, 5, 6, 7, which is going to land us here. So I counted 7/4. And I'm just getting rid of this. I was just using that as a guide, right? So this angle right here is going to be theta equals 7 pi over 4. The angle that lands or lives in the fourth quadrant. And it makes sense because look, if we went 8 pi over 4, 8 over 4 is 2, and we would have landed at 2 pi. So now let's look at D. So for D, we're in degrees now, so I want to go 45 degrees. Now remember, quarter of the way is 90, halfway is 180, 3/4 of the way is 270, one full revolution is 360. So 45 degrees is halfway to 90, right? So I'm going to sketch an angle, right, in the first quadrant that is going to land halfway between 0 and 90 degrees. That's going to be a 45-degree angle. Let's look at part E. We want to sketch an angle of 120 degrees. Now, quarter of the way is 90. Halfway is 180. 3/4 is 270. And then one full revolution is 360. Where would 120 be? 120 is going to be between 90 and 180, right? It's 90 plus like another 30 degrees. So imagine going a quarter of the way and a little bit more. Like another 30 degrees more. So this is going to be an angle of 120 degrees. It's going to live in the second quadrant, the terminal ray between 90 and 180. And we'll do one more. Let's look at D. So now we have, which is really F. Sorry, it should have been F. So theta equals negative 225. So here's 0 degrees, but we're going clockwise because it's a negative angle. So this is going to be negative 90, negative 180 degrees, negative 270, and then negative 360 would be one full revolution. We want negative 225. So that's going to be past negative 180, but not quite negative 270, right? It's going to be between 180 or negative 180 degrees and negative 270 degrees. So it's going to look like this. So theta equals negative 225 degrees. So it's going to be that clockwise angle that's formed, and it's going to end up in the second quadrant between negative 180 degrees and negative 270 degrees. So that's how we can sketch angles in a standard position. And we'll be doing plenty more of that. So here's just a nice sketch of positive angles here on the left. If we were to make a counterclockwise rotation, some of our common angles, 30, 45, 60, 90. And then if we were to add 90 plus 30, 90 plus 45, 90 plus 60, and so on. So we would have 120, 135, 150, and so on and so forth. So this is just what our angle measures would look like. And then on the outside, we have the radian measure along with it, the appropriate radian measure. And then here we just have our negative angles if we were to open clockwise, starting at 0 degrees. So two angles that have the same initial and terminal sides, but possibly different rotations, are called coterminal angles. So for example, let me give you an example of coterminal angles. Let's say I had an initial ray here, and then let's form a 30-degree angle. So let's say this is 30 degrees. If I were to sketch an angle that's 390 degrees for, let's just say, so remember, one full revolution is 360 degrees. So imagine I wanted an angle of 390. I would have to do one full revolution, that's 360, but to get to 390, I would have to do another 30 degrees, and I would land here on the same terminal ray as 30 degrees. So you see how an angle of 390 degrees shares the same terminal ray as an angle with 30 degrees. So they're called coterminal. If two angles share the same initial and terminal sides, but if they're possibly different rotations, right? This one happens to be a rotation and then some. They're called coterminal angles. So really you could get a coterminal angle for an angle by either adding 360 degrees or taking away 360 degrees. So look at this example here. So example 5. Assume the following angles are in standard position. Find a positive angle that is coterminal with each of the following. So if we have an angle of 60 degrees, that's going to be an angle of 60 degrees is going to be a little less than 90, right? Let's say this is 60 degrees. It's going to live in the first quadrant. But if I add 360 to that, right? If I add 60 degrees plus one full revolution, which is 360 degrees, I'm going to get 720 degrees, right? 60 plus 360. I'm sorry, 420 degrees. I can't add right now. Where would 420 degrees be? Well, look, start at your initial ray. Let's do one full revolution, which is 360, but 360 plus another 60 is 420, right? But look where it's going to land me. It's going to be the same terminal ray as 60 degrees. So a 60-degree angle and a 420-degree angle are coterminal angles because they share the same terminal ray. That's the definition. What about what's coterminal with a 150-degree angle? So 150 degrees is going to live in the second quadrant, right? It's more than 90, but less than 180. So let's say this is an angle of 150 degrees. If we add 360 to that, so take 150 plus 360, I'm going to get 510 degrees, right? If I take 150 plus 360 is 510. So an angle of 510 degrees is going to be coterminal with an angle of 150. So I'd be making one full revolution, that's 360, right? Plus if I go another 150 degrees, it's going to land me at the same terminal, right, as 150 degrees, and that angle would be equal to 510. And then let's do one more. What if I have a negative angle? So here's 0, here's negative 90, negative 180, negative 270. So a negative 30-degree angle is going to live in the fourth quadrant, right? Negative 30 degrees, because we have to open clockwise. But I want to find a positive angle that's coterminal with negative 30 degrees. So I could have subtracted 360, but then I would have had a negative angle that's coterminal. I want a positive angle. So just take negative 30 and add 360. So negative 30 plus 360 degrees is going to be 330 degrees. So an angle that's 330 degrees is going to have the same terminal ray as an angle with 30 degrees, right? Because I'm going to go in the counterclockwise direction because I want a positive angle. And if I go here, right, that's going to be an angle of 330 degrees. So we're stopping 30 degrees short of 360, right? And later on, we'll see why coterminal angles are important. So let's just do one last example. Let's just go back to that relationship that we were looking at before. So remember, if we take the arc length and we divide it by the radius, right? S over R, just like we were doing at the beginning of this lecture. So just to go back for a second, not to make you nauseous, but remember, theta is equal to S over R radians, right? That's how we get the angle measurement in radians. We just compare the arc length to the radius. But what if I wanted to solve for R? I could solve for R, right? I would just have to divide both sides by S. Or what if I wanted to solve for S in this equation? I would multiply both sides of the equation by R. So we could use this relationship to also solve for S or R if we knew what theta was, right? Because look, if I have if I have theta equals, let's just use this over here, S over R, look what would happen if I were to multiply both sides by R. R over R is 1, so I would have S is equal to R times theta. Same relationship, right? I'm just solving for S instead of theta. So look at example 6. A circle has a radius of 6 inches. Find the length of the arc. So now I'm not asking for the angle. I want the arc length. If the angle that's formed, so now I'm telling you the angle is pi over 4 radians. And let's express our answer in terms of pi, and then we'll also plug it into the calculator and go 2 decimal places. So let's just look at this picture. Let's use this picture here. So it's like, imagine a circle has a radius of 6 inches. Or you know what? We'll sketch our own circle over here so that one doesn't get too crowded. So here's my circle. Here's radius R, which is equal to 6 inches. We're going to form a central angle of pi over 4 radians. So let's say we form this angle, which is pi over 4 radians. The question is, what is the length of the arc? What's the length of this distance that's formed by the arc here when we open that angle to pi over 4 radians in a circle with radius 6 inches? What is this equal to? And that's just S. Remember, S stands for the length of the arc. And we know that if we want to solve for S, S is equal to R times theta. But very important, remember, theta is in radians. This angle is in radian measure. So let's take the radius, which is 6, and we're going to multiply that by theta, which is, I'm sorry, that should be pi over 4, not theta over 4 in the picture. That's equal to theta. So we're going to take 6 and we're going to multiply it by pi over 4, which is 6 pi over 4, which is going to be 3 pi over 2 radians. And then let's also round our answer to 2 decimal places. So let's type in 3 pi over 2 in the calculator. So let's take 3 and then seconds and then the exponent key, that's pi, and then divided by 2. So there's 3 pi over 2. Which is about 4.71. And I'm sorry, this is not radians. As I'm doing this, I'm like, why am I calling these radians? This is the length of the arc, right? So the length in this case is in inches. So this is 3 pi over 2 inches, which in the calculator, we just converted to about 4.71 inches. So 3 pi over 2 inches is approximately 4.71 inches. So that's the distance of that arc length. And let's do one more. B says a circle has a radius of 4 centimeters. Find the length of the arc intercepted by a central angle of 60 degrees. Express the arc length in terms of pi, then round your answer 2 decimal places, just like we did. So I'm just going to draw a new picture for this one. So here's my circle. Here's my radius. And in this case, my radius is 4 centimeters. And we want to find the length of the arc intercepted by a central angle of 60 degrees. So let's say this is an angle of 60 degrees. The question is, what is this arc length? What's the length of this arc? So what's S? And we know that S is equal to the radius times the angle. But remember, the angle has to be in radian measure. This angle here is in degrees, right? It's 60 degrees. So we have to convert it to radians. And remember how we do that. So look, we're going to take the radius, which is 4, and we're going to multiply that by 60. But in order to convert to radians, remember, we take the degree measure and we multiply it by pi over 180. So it's 4 times 60 times pi over 180. So that's going to be in radian measure in terms of leaving, our answers in, not in, I don't know why I keep saying in radian measure, in terms of pi. So this is 4 times 60 is 240 pi over 180, which is 4 pi over 3, and we're in centimeters. So 4 times 60 is 240, right? So we get 240 pi over 180. And then 60 goes into 240 4 times, 60 goes into 183 times. So it's 4 pi over 3. And my units are centimeters because we're talking the length, right, of the arc. And let's just plug that in the calculator. So in the calculator, 4 times pi divided by 3 is going to be about 4.19 centimeters. So it's about 4.19 centimeters. And that wraps up our first section on trig. So really the purpose of this section was just to reintroduce you, because I know at some point you've seen a little bit of trig, you've worked with angles. So just how to interpret an angle in terms of a circle, right? If one full revolution is equal to 360 degrees, the difference between turning clockwise and counterclockwise, and then, how do we, interpret degrees and radian measure? How do we convert back and forth? And then also, this is important, how to find arc length, right? Based on a radius and a central angle measure. So our next video will cover section 1.2 of trig.